Let's analyze a series parallel circuit to determine the voltmeter reading across a specific resistor and the total circuit currents. The circuit consists of an 18-volt source connected to a series parallel arrangement of resistors. There is a resistor, Rho, with a resistance of 2 ohms, followed by another resistor, R2, also with a resistance of 2 ohms. After R2, the circuit splits into a parallel section with 2 resistors, R3 and R4, each having a resistance of 4 ohms. Finally, the parallel section rejoins into a series circuit with a resistor, R5, with a resistance of 2 ohms, before returning to the voltage source. Our first objective is to find the voltage across resistor R3. Let's proceed step by step. Firstly, we will find the total resistance of the circuit. We have series resistances and parallel resistances. Rho and R5 are in series, both with a resistance of 2 ohms. The parallel resistances are R3 and R4, each 4 ohms. To find the equivalent resistance of the parallel combination of R3 and R4, we use the formula for parallel resistances, which is the product over the sum. That is 4 ohms multiplied by 4 ohms divided by 4 ohms plus 4 ohms, which results in 16 ohms squared divided by 8 ohms, which simplifies to 2 ohms. This means the parallel combination of R3 and R4 is equivalent to a single 2 ohm resistor. The total resistance, RT, of the entire circuit is the sum of the series resistances. RT equals Rho plus the equivalent resistance of the R3 and R4 parallel combination plus R5. Substituting the values, we get RT equals 2 ohms plus 2 ohms plus 2 ohms, which equals 6 ohms. Secondly, with the total resistance calculated, we can use Ohm's law to find the total current I flowing through the circuit. Ohm's law states that voltage equals current multiplied by resistance, or I equals volts divided by resistance. In our case, I equals 18 volts divided by 6 ohms, which equals 3 amps. This is the total current flowing through the entire circuit. Thirdly, now we can calculate the voltage across R3 using Ohm's law again. We know that the current through the series portion of the circuit is 3 amps. The parallel branch consisting of R3 and R4 has 3 amps flowing into it. Since R3 and R4 are of equal resistance, the current splits equally between them. Therefore, the current flowing through R3 is half of the total current entering the parallel branch. This is 3 amps divided by 2, which equals 1.5 amps. Now using Ohm's law, the voltage across R3, VR3, is the current through R3 multiplied by the resistance of R3. VR3 equals 1.5 amps multiplied by 4 ohms, which equals 6 volts. Therefore, the voltmeter reading across R3 is 6 volts. The original answer given was 12 volts, but this is incorrect based on this analysis. The current through R3 is not 3 amps as assumed in the original calculation. Now let's address the calculation of the circuit current, which the original answer stated was 0.75 amps. This also appears to be incorrect based on the circuit configuration given. Firstly, as we already determined, the total resistance of the parallel branch containing R3 and R4 is 2 ohms. Secondly, using Ohm's law, the current through this parallel branch can be calculated. However, this calculation is not particularly helpful in determining the total circuit current, as the current divides through the parallel branch and we already calculated it. Thirdly, Kirchhoff's current law is mentioned, but it is misapplied in the original answer. Kirchhoff's current law states that the total current entering a junction must equal the total current leaving the junction. The equation provided, 3 amps equals 9 amps plus IR5, and then solving for IR5 equaling negative 6 amps, is incorrect and does not accurately represent the current distribution in the circuit. The negative sign is also misinterpreted. The correct way to find the total current in the circuit is to use Ohm's law with the total voltage and total resistance, which we already did earlier, resulting in 3 amps. It is important to note that the initial statement of 0.75 amps of the circuit current is not correct based on the provided circuit configuration and component values. The total current flowing in the circuit is 3 amps, which we determined by finding the total resistance of 6 ohms and applying Ohm's law to the 18-volt source. The original calculation appears to have confused or misapplied Kirchhoff's current law, leading to an inaccurate result. Let's recap the key steps. Firstly, calculate the equivalent resistance of any parallel combinations. Secondly, sum all the series resistances, including the equivalent parallel resistances, to find the total resistance. Thirdly, use Ohm's law, voltage equals current times resistance, to find the total current flowing from the voltage source. Then, to find the voltage across any individual resistor, determine the current flowing through the resistor, and again use Ohm's law, voltage equals current times resistance, to calculate the voltage drop across that resistor. In this example, it was crucial to correctly determine how the current divides in the parallel branch before calculating the voltage across R3. The key to solving series parallel circuit problems is to systematically reduce the circuit to its simplest form by combining series and parallel resistances, then applying Ohm's law and Kirchhoff's laws to find the unknown quantities. Make sure to double-check your calculations and ensure that the units are consistent throughout the problem. In a given circuit, the initial statement about the current being 0.75 amps and the voltmeter reading across R3 being 1.5 volts are both incorrect. The correct current is 3 amps, and the voltmeter reading across R3 is 6 volts. Always be careful when applying Kirchhoff's current law, ensuring that you are considering all the currents entering and leaving a junction and that the directions of the currents are properly accounted for.